Okay, now let's start. So, hello everyone. Welcome to our virtual academic seminar to celebrate the launch of SmartMath. SmartMath is an open access journal co-launched by Valley and Tianjin University. Today is really our great honor to have Professor Yong Zhu here to give us a seminar talk. Before that, please allow me to introduce him first. Professor Yong Zhu is a Andrew Adams Distinguished Professor in the Department of Mechanical and Aerospace Engineering with affiliation in Biomedical Engineering and Material Science and Engineering at North Carolina State University. He received his bachelor degree from the University of Science and Technology of China and a master and a PhD degree from Northwestern University in USA. After completing his postdoc training at the University of Texas, Austin, he joined North Carolina State University in 2007 as an assistant professor. His group conducts research at the intersection of mechanics and materials and micro nanotechnology for stretchable and wearable electronics. His work has been recognized with many prestigious awards, including Best Research Award from Humboldt Foundation, James R. Rice Medal from Society of Engineering Science, and the ASME Cell Nemeth Lasser Annual Career Award and the Gustav L. Larsen Memorial Award. So today is really our great honor to have him here to share us a story entitled Recent Advances in Silver Nanowire-based Stretchable and Wearable Electronics. So without further ado, Professor Zhu, all floor is yours.
Okay. Thank you very much, Jun, for the kind introduction and also taking the time to host my talk today. I know it's a busy and important day for you. Okay, thank you. And also, I would like to thank SmartMath for the very kind invitation. Okay, so let me share my screen. All right, you can see my screen now?
Yes, I can see, yeah.
Okay, great. Okay, I will get started then. Hello, everybody. Well, good morning, good evening, depending on where you are. It's really a great pleasure to give the talk on this lecture series. So I'm going to talk about the recent advances in silver nanowires based on stretchable and wearable electronics. Okay, so recently we have seen a tremendous amount of work in the area of flexible, stretchable, wearable electronics. Okay, so I'm going to just share some of our recent work along this line. So this cover art basically captures what I'm going to talk about today. Okay, so I will start with materials. Materials about stretchable materials. So for instance, in this case, I'm going to focus on the nanowires. Okay, then I'm going to talk about a variety of wearable sensors. For instance, on this cover art, we have, let's say, EKG electrodes, right, to capture the electrocardiography. We also have wearable heaters and so on. Okay, but then manufacturing is a very important issue. Okay, it's an enabling technology to really propel this field. Okay, so in this case, you can see we are showing something called the Electrohydrodynamic Printing technique. Okay, and then I'm going to talk about some recent work on recycling of nanowires. Okay, for a sustainable future, and also some recent exploration of some of the applications. So let's talk about stretchable electronics, right? So material, well, then two ways, right? One is you have materials that are intrinsically stretchable, right? If you don't, then it's possible to make stretchable architectures or structures out of the material. So in this case, this cartoon shows a wavy shape, right? Accordion bellows. So that's just one example. There are many other type of stretchable structures. In terms of fabrication, there are two approaches also. The first one is called a top-down approach, basically microfabrication, right? We have seen some big names in the field, okay, using the top-down microfabrication. And then also the other one is called a bottom-up approach. So essentially using assembly of nanomaterials. So here we have examples from Takao Somaya. This is a carbon nanotube composites, and then John and Boss group, right, depositing carbon nanotubes on top of an elastomer substrate. And also this is a stretchable graphene electrode from Samsung and Sungkyuan University in Korea. And this is Yong Zhu's group in Korea. So essentially assembling nanoparticles into a stretchable structures. Okay. So as I said, I'm going to talk about a silver nanowire. Silver nanowire recently have become one of the promising contenders, right, in this arena, okay, in terms of stretchable materials. Okay, but silver nanowires was actually a very promising material for a transparent and flexible electrodes. Okay, a material considered as an alternative to ITO. Right, for instance, here I'm showing this. A touch panel from company at Cambridge. Okay, and then this is the work from G.B. Pace group at UCLA. So they use the silver nanowire electrodes in the dielectric elastomer actuators. Okay, but mostly the silver nanowires were used as transparent or flexible electrodes. I think our group was among the first to use this to develop this silver nanowire based highly conductive and highly stretchable conductors. So was around the time about 2012. So the method is very simple. Okay, so you just drop cast the silver nanowire solution and then you form this nanowire network structures. Okay, and then you coat a layer of elastomer material like a PDMS on top, right? Liquid in the liquid state, and then the PDMS infiltrates through the nanowire structures, and then let it dry. You peel it off, right? Then you form a composite structures, and then so in that case, the nanowires are below, right, under the surface of the elastomer, right? And then what we can see from the cross section here. And then this layer, well, this composite layer, right, is highly conductive, and then there's different ways to print them and so on. Okay, and you can see the resistance versus the strain. Okay, resistance is nearly independent of strain. Okay, you can stretch multiple times, but it's independent of strain. So that's a really ideal, a stretchable conductor. Right? You want to maintain a constant resistance. Okay? But I want to talk a little more about this is stretchable conductor, the mechanism. Okay, so here I'm showing the resistance versus the strain curve. Okay, so the resistance, this is the first stretching. Okay, so the resistance increase almost linearly with the strain. Okay, and then when we release and then stretch again, you see in the second time, this is the second stretch, the resistance is nearly constant, right? Again, that's what we wanted. But what happens, right? Why the second and the first is very, very different, and also the stretch and the releasing behavior is also very different, right? So we propose this mechanisms. Okay, so here shows the composite structures, right? Nanowire, PDMS, and then when we stretch, what happens is initially, in a small strain, initially there'll probably be some elastic deformation, okay, between the nanowires and between the wires and the matrix, okay. And then if you stretch further, right, in this case, like 80%, then there for sure there's a sliding between the nanowires and also between the wires and the matrix, okay. And then when we unload to about 50%, what happens is, well, there will be some recovery from the elastic deformation, right? And then when you release it further, then what happens is, as we said, right, here about millions of nanowires, right, there's a sliding between them. But when you release them, you see these millions of wires, they're not going to go back. It is very difficult to go back. Well, energetically, right, it's very expensive to go back. And then the material is very smart. They say, hey, let's not go back, but instead collectively, let's buckle out of plane. Well, they will be introduced some bending energy and so on, right? But energetically speaking, is actually less expensive than going back because you have to overcome all the frictions to go back. So materials are smart in this sense. Anyway, it forms these wrinkle structures. And then that's what we want, right? This is very important, like a very similar to the accordion bellow structure we talk about, right? So what happens is when you stretch, let's say in the second stretch, what happens is you essentially flatten this wavy structures without further sliding between the wires or between wires and the matrix. Then that's why there's no resistance change. Okay, so this mechanism actually we have sort of observed it. Here, this is because it's embedded, it's hard to see. But we observed this in the case of carbon nanotubes in earlier work. So we have carbon nanotubes on the substrate. We stretch them. We see the sliding between the nanotubes. Okay, sliding between nanotubes, and then when we release them, the nanotubes, they don't go back straight. Instead, they also buckle. It's a slightly different way of buckling. This is buckling in plane, but otherwise the mechanism is very similar. And also, if you look at this resistance versus strain behavior, is also very similar. Right? When you release, it nearly goes constant. Okay. And then what we talk about is Barconi mechanism or ring coning mechanism, right? We also see that actually from the cross-sectional SEM images. You see the nanowires, when we stretch, release, they do form this ring coning structures, okay? And then around about the same time, there's another group from Seoul National University in Korea. So they found that the long nanowire population nanowire also enhances stretchability. That's basically saying that the longer the nanowire, the better for the stretchability. So think about that time, I think these silver nanowires started receiving a lot of interest as stretchable or stretchable conductors. Okay, and then a few years later, with my former student Shen Yu, now is assistant professor at Stony Brook University. So we wrote a review articles essentially summarizing a variety of nanomaterial enabled stretchable conductors, right, from nanoparticles to nanotubes, nanowires to the materials and so on. Okay, and then with some applications. So maybe let's take another look here. Right, we said that there are two ways, right? Either top down or bottom up. Right, so this is a top down, or in terms of materials, you have thin films, right? You pattern the films. Okay, and then the nanostructures essentially assemble them somehow. Okay, the fabrication, microfabrication here using printing technique. And then in terms of the material properties, well, for thin films, largely known, okay, because it has been studied for decades. Okay, and then for the nanomaterials, actually a lot of the basic properties are largely unknown. I can speak in terms of mechanical properties. Okay, we know quite some, but still a lot are not known in terms of elastic property, in terms of plastic property, fracture properties, all the size-dependent properties. A lot actually are still to be quantified. Okay, I would assume maybe similar in the case of electrical optical thermal properties and so on. Okay, and also an important difference is the thin films, they are continuous, okay, or the structure continuous. But if you look at the nanostructure here, they are discrete. They're discrete, okay, or something we call a population network. Okay, so this actually gives an inherent advantage in terms of recycling. Okay? It is very easy, right, straightforward to recycle, let's say, a network structure, right? Essentially, you just separate them into individual ones, you put them together. It's very easy. So it's something I'm going to talk about towards the end of the talk today. Oh, okay, I was talking about the properties can be different, right? Property can be different. So I will give you one example for mechanical properties. Okay, so mostly the silver nanowires we use in the solution synthesis, right, is the pentatwin nanowires, because you have 5 twin boundaries along the length of the nanowires. So yeah, so we have a cross-sectional TM clearly shows the 5 twin boundaries. So what happens actually here, quite interesting. Here it shows a strain behavior. What happens? Well, you have an elastic deformation, and then you have some plasticity and so on. But then you causing the relaxation, and then when you unload, but what happens? Very interesting is the recovery. You see, the plastic deformation can be recovered. Okay, so something we call it the recoverable plasticity. The reason is for all these nano structures, almost always the dislocation is nucleated from the surface. But in this case, you have twin boundaries. They will block the dislocations, and then when you unload, and then the dislocation will go back. Okay, so but think about that's good, right? That's advantages for stretchable electronics. When we stretch them, they will deform, but when we release, they can come back. So the nanomaterial is this is some ring coning structures I was talking about, right? But also the nanomaterial itself has excellent mechanical properties. It also helps in terms of the recovery, okay, in the structure, right? That's important for stretchable electronics. Well, here this is another case. In this case, you have a single twin boundary, okay, along the length, so we can see clearly. So this is in situ TEM. We can see the dislocation nucleated, blocked by twin boundaries, and then disappear and all that, right? So yeah, if you're interested in the mechanics details, you can refer to these papers. Okay. So now let me talk about the second part, the wearable sensors. Okay. So people have developed a large number of wearable sensors using silver nanowire. Well, as I said, here I'm going to focus on silver nanowires, but many other nanomaterials, right? Nanotubes, graphene, 2D materials, and so on. Okay, so in many aspects, for instance, from the activity tracking to electronic skin to personal healthcare. So I'm going to talk about a few examples from my group. So the first one is a wearable called a multifunctional sensors. Okay, so this is a sensor array. Okay, you can see that it's multiplexing sensor array. But the mechanism is quite simple. Essentially, it's a capacitor. Okay, so we have two electrodes. We use the silver nanowire, right, as the top and the bottom electrodes, and then you put a dielectric material in between. Okay, so as a strain sensor, okay, what happens is when you stretch it, the overlap area increases and then the gap decreases, right? Both contribute to increasing capacitance. Very similar for pressure sensor. When you press it, the same thing, right? The capacitance will increase. But it also can be used as something called a touch sensor. Touch sensor is different from pressure sensor. Pressure sensor, physically, you mechanically, okay, you press it, right? So called a touch sensor, you don't actually touch it. You just come very close to the sensor, and then using a conductor, for instance, our fingertips, right? A conductor. So the conductor is going to disturb the electric field, then causing the capacitance change. Okay, so with the same configuration, right, same capacitive sensor, we were able to achieve actually all three. Okay, so I'm going to talk about one particular case. This is the capacitive sensor. Okay, capacitive sensor. So and then this is the capacitive sensor behavior. So the capacitance change is linearly proportional to the strain up to 150%. Is a huge strain, right? And then it's totally reversible. We did a loading, unloading, right? Totally reversible. So that's the major advantage of capacitive sensor. Okay, capacitive sensor. It has downsides, but these are the major advantages, which is very important for mirroring large deformation. For instance, deformation from our joints, right? Like a finger knuckles, right? Like knees, elbows, right? Where you have large deformation, the strain can be as large as 50% or even more. Okay. So in this case, we calibrated our sensor. We calibrated our sensor using the gold standard methods for deformation measurements. Okay, so essentially you put these optical markers, okay, and then with multiple cameras. Okay, so here we did this. Oops, sorry, we did with this test. So the strain, this one, the blue comes from our strain sensor, and then this angle is actually coming from this optical method. Okay, optical method. So we tested on two groups of people. The top A is from the healthy subject. You can see, and then just bending the finger and that causes multiple times, right? Multiple times. You can see the strain measurement and then also this optical measurement. They're almost perfectly matching. So it says about the accuracy, about the response speed of our strain sensor. Okay, and then this panel B is about a stroke subject. Right? For stroke subjects, you see the motion is a little involuntary. You can see some more complicated patterns, right? Some jerky motions and so on. But again, you can see, look at these details, fine details. You can see still our strain sensor can capture all these fine details. Again, show excellent correlation. So the sensor works, very, very well. We can put it on other joints like knees here, right? So you can do this so-called Patellar Reflex experiment. You hammer your knees and then it will kick automatically, right? You can capture the details. You can see maybe with the eyes, but you may not be able to capture the details such as the amplitude, such as the repeatability, such as also the time response and so on, right? So these details could tell you about your nerve. Okay, about the nerve, how well the nerve functions. Okay. And also with the knees, we can capture the daily activities, right, from walking to running to jumping and so on. Okay. The next one is a temperature sensor. Well, temperature is important to measure, right? But it also sounds straightforward. We just measure temperature, right? So we use this called a thermal resistive effect. Basically, the resistance changes with temperature. Okay. So for that, there are two requirements. One is, well, you need to have a high so-called temperature, a coefficient of resistance, right, to be more sensitive. And then perhaps more important, it has to be strain insensitive. Okay, so let's talk about this. And then, well, we look at a couple of things. One is the annealing. Okay, so we have this percolation network, right? This is as prepared, okay, but basically van der Waals interactions. And then we can anneal them. When we anneal them, we actually found that this is so-called TCR. Right, the temperature coefficient of resistance actually increases with annealing. Okay, so we found that 200 degrees C is the best we have. Okay, and also the nanowire density also matters. Okay, so if the increase in density also leading to a larger TCR. Okay, but we said the strain it cannot, because this is for wearable applications, right? Inevitably, we're going to have some strain. But the strain is detrimental to this type of resistive sensor, because a small strain can cause a huge resistance change, okay? Huge resistance change. So we have to somewhat isolate the strain or reduce the strain. So we use a kirigami structure to achieve that. So essentially what this is the sensor basically, okay? And then when we stretch it, you see all these ligaments, they deform out of plane, okay? And then we perform the finite element analysis. For 100% strain, applied strain, the local strain is very small. It's in the range of minus 0.5 to about 0.5%. Very, very small, you can see. Okay, so that's why actually we also measure the resistance change. You see the resistance change is nearly zero, almost zero. Okay, so that is very, very important, because as we said, if you want to measure the temperature, you have to isolate. You have to isolate the effect of strain, okay? Because the strain effect can easily overshadow your temperature effect. Okay, all right. And then yeah, we have a demonstration. We put this on the for the workout. Okay, during the workout, actually our muscles heats up. Okay, so so we can measure that. Okay, it's about 2 degree warm up. So we have this our sensor, and then also we calibrate with a conventional thermometer. Okay, so it works pretty well. And then also this electrode, because we said that this material is highly conductive, right? So we just use it as electrode. Well, there's some, this is the commercially used, right? 3M electrode. You may see this in the hospital. So okay, it has a gel layer, which is important to ensure the quality of the electrode, the skin interface, but that causes some problem like skin irritation. So there's strong need to do this so-called dry electrode without the gel layer. Okay. So this is our first work on this, and then essentially we see this is the wet electrode, commercial one. This is our electrode, very much comparable, the signal. And then during this is when the subject was sitting, and then when the subject was moving, actually the motion, so-called motion artifacts is quite a problem for the electrodes, okay, because the electrode is going to move relative to the skin, okay, causing noises. So in that case, our actually is better outperform that. It's because we have a more stable interface. Okay. Hydration is also very important. Okay. I think I'm not going to talk about the details. This essentially is measure the impedance. Okay, measure the impedance, because the impedance will increases with more water in the skin, and then the impedance will decrease. Okay, the impedance will decrease. So we were able to capture that, and then we can indicate the hydration level of the skin. And then here we did a sort of integration. We put the multiple sensors together. Okay, multiple sensors. We have EKG electrode, hydration sensor, also the strain sensor. Okay, and then we integrated also with the electronics. So we have the electronics. So this is basically the electronics. Okay, it has the signal conditioning, so signal acquisition, a conditioning circuit, and also Bluetooth for wireless communications. Okay, so this is the entire thing. You have the sensors here, and then we put the electronics and the Bluetooth and so on in a small package. Okay, also the battery in the package. Okay, maybe the last one here. Yeah, we also develop something called antennas, right? Antenna, a couple of types of antennas. So antennas are very important. Antennas are relatively simple in terms of the electronic functions. Essentially, it is something conductive. Okay? You have two conducting layers. Okay, so this one received quite a lot of interest because it shows high performance. Because again, right, it's for the soft antenna, our electrode, right? It's the antenna performance depends on two things. One is the conductivity, high conductivity of the conductor. Two is the loss of the dielectric layer. Okay, you want to have less loss. Okay, so anyway, because of this thing is very conductive, right? So we were able to achieve some high performance conductor. Well, here, I showed the student, Ning Lanson. She is actually an undergraduate student. She basically did this work during her visit for the summer research. Okay, just in the summer, so it's quite impressive. So just particularly highlight her contribution here. And also we continue collaborate with Penn State group. Yeah. So this is a very simple design, but by more complicated design, more sophisticated design. Okay. So we were able to do this called a circularly polarized antenna. Okay. So then we can further improve the efficiency. For instance, we were able to achieve like 80% efficiency, according to our collaborator. This was the world record at least a few years ago, okay, in terms of the efficiency for flexible wearable antennas. Okay, so also we have with Stretch and Yong, so we also wrote a review paper, okay, for wearable sensors, nanomaterial enabled for healthcare applications. Here we list a number of sensors and also the integrated multimodal sensors and so on. Okay, so if you're interested, please refer to this review paper. Okay, so all right, we have the materials, we have the sensors and so on, but manufacturing is very important, right? If you are talking about something serious, you get to talk about manufacturing. Okay, it is a step. It is a step we have to work with. Okay, so here we have some new materials, right? They're soft, stretchable, and all that. So they're presenting also some challenges for manufacturing. So anyway, for manufacturing, well, let's say you started with a few steps, right? You need to have the ink formulation, right? But also I talk about different types of printing techniques and also post-printing treatment. Okay, so here manufacturing. Let's see. So we have done a couple of different methods. Okay, one is called Electrohydrodynamic Printing. Okay, this is very similar to inkjet. Okay, by the look. Okay, but the inkjet is this will be the inkjet. The inkjet, the problem is the nanowires. Inkjet, right? It's good to print, let's say, commercial inks, typically made of silver particles or flakes, right? But with nanowires, these wires are long, right? They are 20, 30 micrometer or even longer, right? Remember, we said actually the longer maybe the better in terms of stretchability and so. We want them to be long, but then it causes problems, right? They could clog the nozzles. Yeah, they could clog the nozzles, right? If the nozzle is small, you want to have high resolution of printing, right? So you cannot have a too big of a nozzle. So that's the dilemma. And so we can sort of approach this problem using this method. But essentially is we apply a voltage across the printer head and the substrate. Okay. Otherwise, it's very similar to inkjet. But with this voltage, it helps. Well, it's quite complicated, the mechanism, but in short, essentially it forms something like a Taylor cone. It's a Taylor cone. You could have a big nozzle. Okay, but it will shrink. The droplet will shrink, and then what you print is actually pretty fine in terms of size. Okay, you have a big nozzle to avoid the agglomeration problem, right? As we said for nanowires. But then you can, with this Taylor cone, you can still print fine features. Okay. So we were able to print something like, the resolution is about 45 micrometer, and then the conductivity is also very high. This is a very high conductivity in terms of a stretchable electrode. Okay, it's very high conductivity, and then we did the careful studies. Okay, we look at the effect of the concentration of the so-called different printing parameters, including speed and so on. Okay, quite interestingly, probably not surprising. If the printing speed is high, well, in the center is you always have a good alignment, but typically on the edges, you have less alignment. Well, especially so for the low speed. Okay, for the low speed, the center is reasonably aligned, but the edges are not aligned. But for the high speed, okay, so the center of course is still aligned, but the edge is also better aligned. Okay, so that's not surprising, but it can be helpful, right? So you can the printing speed can help us to adjust the alignment. The alignment is also important, right? The structure can have important implications for the properties. And as demonstrations, we printed some rather complicated features. This is a fractal pattern. We use the fractal pattern as a heater, right? The heater can cover relatively a large area, can still provide a uniform heating. And also we printed a EKG electrode. So in this case, you can see it's sort of transparent, or at least semi-transparent, right? Because we don't have a solid structure. Okay, so we have this fractal pattern structures. But if you look at here again, we use the 3M commercial electrode, and this is our Sliver Nanowire electrode. And if you compare, pretty much very similar in the signal qualities. Okay, so this printing method is great, right? It can achieve low resolution. Well, I also, oh no, we address all these issues. This was the challenges. Okay, low resolution. Okay, so this address conductivity is also addressed by this method, and the quality is also very good. Right? So address all the first three challenges, right? So to print in the stretchable electrode, but low throughput, we still haven't addressed that issue because this is a sequential process. You can imagine, relatively slow process, right? Then we looked at another method called gravure printing. Okay, gravure printing, well, simply put, you see here we have a intaglio change. Okay, so then you put this inks. Okay, you first of all using the Dr. Blade to put the inks into the change, and then here this is the substrate you want, the flexible substrate you want to print on. Okay, and then you essentially press the inks onto the flexible substrate. You roll the substrate and then print on. So this is basically the technique people use for printing newspapers. So you can see this can be high throughput, high speed, okay? And then also it can be integrated with row-to-row printing, right, to further enhance the speed, okay? So this was, yeah, really for larger scale manufacturing. And then we're able to, get a reasonable quality resolution, okay, and also conductivity, and then we can print different types of structures, including crossbars and so on. So, okay, talk about the two methods, and also we'll talk about some textile integration, because textile is a natural substrate, right, for wearable electronics. Okay, but then how to integrate this nanowire-based devices with textiles. Okay, so there's the different efforts on that. Okay, so this is represents ours. So what we have is, well, let's print the we just drop cast the nanowire network, right? So in this case, instead of using PDMS, we use the TPU. TPU is the thermoplastic polyurethane. Thermoplastic polyurethane, and then we use the laser scribing. We use the laser to pattern the device. Okay, and then after that, we put this device, and then we heat and press. We laminate, essentially laminate to a fabric, to a textile substrate. Okay, so the TPU here serves sort of dual purpose. One is provides a stretchable substrate, but also provides a sort of structural adhesive. Okay, adhesive under this pressure and heat. It forms a strong bonding with the textiles. Okay, and then here, yes, showing you a few devices. We printed this spiral pattern as a heater, and then this fractal patterns for electrodes. Okay, for this several electrodes, we print on the top and the back and so on. Okay, then you can see this is the textiles, very flexible. We can easily deform it and so on. Okay, and then here we demonstrated two types of electrodes, right? EKG electrode. Okay, EKG electrode. We have a sensor on the outside. Also, we have a sensor in the inner side. Okay, inner side, and then by touching this one, right, by this essentially the two electrode configuration, so we can measure the EKG electric signal. So this again, this is the 3M commercial electrode. This is our electrode again, right? Very much comparable. We always just a benchmark comparison with the commercial electrode here. And then here we have EMG electrode. This is electromyography, okay, to measure the muscle activities. Okay? When the muscle contracts, it generates electricity, generates voltages. So we can measure this also again, commercial electrode, our electrode, very much comparable. And also strain sensors. Okay, strain sensors. Okay, so with this sensor, we can put this on a joint like elbows. Okay, like elbows here. Right. So you can see we can capture the strains, okay, at either fast or slow motions. And if suppose here, right, this could be used for sports applications, right? You like playing basketball, right? Or you play a baseball, or you play many sports, right? When your elbow moves, you can capture the bending strain. Well, and then through a simple kinematics model, it can be converted to joint angle. Joint angle is very important for sports performance. Okay, think about it. You can also put this on other joints, right? You can put it on wrist, you can put it on the elbows, knees, and so. Okay. One more challenge in terms of manufacturing, right? So all this we have is a solid substrate, okay? And then for wearable electronics, especially long-term wear, right? You want to have something called a permeable. Okay, You want to, or something so-called a breathable, okay? So breathable substrate, okay? So to otherwise you may have skin irritation if you wear the device for a long time, okay? Essentially you may have a sweat accumulation, right? You want the sweat to evaporate, right? So to put it simple, right? You want to have something like a porous substrate, okay? You want to have a porous substrate, okay? There are different ways to do this. So we use this called a breeze figure method. Okay, this method is very simple and it can easily scalable. So essentially, we have this TPU in this time. We use a solvent called a THF, right? So we coat a film, and then we put this in a very humid environment, and then the water will condense. The water will condense on the substrate, yeah, and then they will self-assemble into droplets, okay, into droplets. Okay, and then they will, when the solvent evaporates and so on, they will essentially form a hose, okay, on this substrate, okay, on the substrate. And then we want to coat the nanowire. We just deep coat this into the silver nanowire solution, and then we heat press. We heat press. So in this case, the nanowires will be heat pressed into the TPU substrate, okay. And then in this case, actually, we have nanowires on both sides, okay, on both sides, right. And then, so we can have it directly on the skin. We can do something called epidermal electronics, right? So we put the reference electrode, recording electrode directly on the skin. And you see what happens is with this porous electrode right now, it's not only highly conductive and so on, and permeable, but also nearly transparent, okay? Nearly transparent, okay? Very high transparency, okay? You can barely see this, okay? So again, we measure the EKG performance. We also measure the EMG, okay? Using this. And also, we sort of explored as an application, we explored something called a human-machine interface, right? That is also a very promising direction for wearable devices. Okay, so in this case, we integrated the device with a textile, a sleeve. So we put on a sleeve, and then we essentially play some computer game. This is a Tetris game, right? The Tetris game, or we use this called a self-capacitance mode. Essentially, you only have an electrode here, and then our finger forms another electrode, okay? It forms another, and then forms a capacitance, okay? And then that can, when you move up and down, right, the capacitance changes, and then you can achieve some functions here. So that was a fun demonstration. So let me show if I can play this movie. Okay. Yeah, this work was done by a visiting student, Weixin Zhou. I think actually this is Weixin, who is having the fun to play the Tetris game. Yeah, this is really cool. I wish I have this when I was younger. Okay, I remember those days I was playing Tetris. It was so fun. Yeah, I usually miss lunch when I play this. Okay, anyway, yeah. So this was a work by Weixin. Yeah, it was very impressive. And also, yeah, we wrote a review paper with Qijing. Yeah, Qijing is a postdoc to summarize the different ways of printing and nanomaterials, and then different types of nanomaterials, okay, for stretchable wearable applications. Okay, all right. So yeah, I'm closing to finishing. So let me talk about a couple of recent works. Okay, so one is on the recycling. Okay, so recycling becoming more and more important because we're talking about sustainable future and so on. Okay, so something called electronic waste. This becomes more and more of an issue, right? Look at we have more and more electronics devices these days, and then oftentimes the electronic devices have less and have shorter and shorter lifetime. For instance, iPhones, right, or other smartphones, or even laptops, right? You don't use it for 5-10 years. Okay, you use for a short life. Okay, anyway, right? You want to get a new ones. So, but all this thing, consider all this will contribute to the enormous problem of electronic waste, right? Electronics waste. So it would be great if we can recycle all these electronic devices, or even partially, right? Okay, so that's the idea, and then that's the motivation. Okay, so this cartoon shows we have soft electronics, right? And then we recycle this. So we dissolve the substrate, and then we can recycle the functional materials. Okay, nanomaterials in this case, and then we can dissolve the substrate. Okay. Okay, here, well, basically the same, but here's a little more details. Okay, so here we have a silver nanowire network, right? And then we put this, we ultrasonicate this in a working solvent, and then to disperse the nanowire network into individual nanowires, and then we can centrifuge to remove, let's say, some particles or remove some broken nanowires and so on. Okay, and then we centrifuge again in ethanol. The ethanol we always use ethanol as sort of the last solvent, just to ensure every time when we drop cast, we have the same solvent, right? And so that's why we have this extra step. We put them in ethanol. So this is now the recycled silver nanowire in ethanol. It's basically the same thing as what we have originally. Originally, right, after synthesis, we have nanowires, silver nanowires in ethanol. Now we recycle them also in ethanol. So it's basically the same thing. And then we can drop cast again and then just reuse. Very straightforward ideas, right? But it's really enabled by the nanomaterials in the form of a network, right? Otherwise, if it's a continuous material, this process will not work. Okay, this is a simple process, will not work. You have to involve much more complicated, much more energetically expensive process. Okay, a couple, some details. Let me go through them quickly. And then this is the okay, so this is the effect of the working solvent. Okay, so we use a variety of solvents. This is the original ones, okay, network structure. This is after we recycling using IPA, EG, and the DI water. Okay, you can see the quality reasonably well. These two, but the DI water is pretty bad. So then we measure the distribution, okay, the nanowire distribution. We define something called the area function, okay, area function, essentially for a small area, for a given unit area, okay, the number of silver nanowires, okay. And then if you do, see, then you can plot this, from there you can sort of know the density and also know the variation. The variation actually tells you about if the distribution is uniform. Right? If it's uniform, then it's going to be very narrow distribution. But if it's not uniform, then you can see you're going to have a wider spread in terms of the standard deviation. Okay, and then we measure the resistance also. After the recycling, measure the resistance. You see using the original and the IPA, and this is the ethanol and so on. Okay, the resistance is good, but using EG, especially DI water, you see the resistance increase a lot. So that is consistent with the fact that with DI water, you see, it's not uniform. Okay, the distribution is not uniform. You have local agglomeration. So okay, so to put it short, so why this IPA works better than DI water? Okay, so it's because of the surface tension. Okay, so with the low surface tension, IPA has low surface tension. Okay, with low surface tension, okay, the working solvent can easily get into the junctions of nanowires, and then when they get into the junctions, then they can help to break the nanowires apart. Okay, but with this high surface tension, then it's difficult to get in. Then you cannot break the nanowire network, right? Okay, and then also ultrasonication is also important, right? Ultrasonication, if you do it too long, and then you're going to shorten the nanowires, right? That's a well-known phenomenon. But if you do it too less, the purpose of ultrasonication is to disperse, right? To form a sort of a uniform distribution. So we have to find a trade-off, right? If it's too short, it's not good. It's too long, breaking the nanowire also not good, right? So this is reflected in the resistance, okay, initially. So we have to find a sort of optimize time. Well, for the power we use is about 20 seconds. And then we can recycle multiple times. Okay, so multiple times, what happens is, well, both problems could occur, right? One is if you ultrasonic multiple times, some more nanowires will become shorter, right? When they become shorter, you see the resistance will increase, right? And also maybe the agglomeration issues can also become more serious, because in addition to the working solvent is still the same, right? We use IPA in this case, but we know for silver nanowire, right? You have a so-called PVP layer on the surface, right? If you wash it multiple times, that layer can get washed off, and then that can lead to the agglomeration. Okay, so anyway, we can do multiple cycles, but the quality could drop. Okay, especially I think we use like 4 cycles. It's okay, reasonable. The resistance is reasonable, but after that, resistance will increase quite a lot. We can recycle the entire device, right? As we said, in this case, the substrate can be dissolved in water, and then we can dissolve the substrate and then recycle the nanowires. Okay? And then we demonstrate some couple of applications. Okay, so just use the recycled nanowires. Okay, using the recycled nanowires, and then the performance is basically the same as the initially regionally synthesized nanowires. Okay, so my last topic, I will spend probably a minute or two to finish that. So you can see silver nanowires, very conductive, stretchable, and then it's easy, right, convenient to process. So they can enable many applications. Two more examples. One, we're using some heaters, and the heater can be used as a thermal actuators and so on. And then also we use as a plant sensors in addition to human sensors on the humans. So this, you can see this is the electrodes, right? It's the electrodes, silver nanowires in the PDMS electrodes. But it's the electrode, any conductor is a heater, right? Based on the dual heating. Okay? So with the dual heating mechanism, so we can get a reasonable heating rate and a cooling rate. And then we bond it. We bond these materials with another material with a very different thermal expansion coefficient. In this case, we use the polyimide. Polyimide is the thermal expansion coefficient is very small. It's only 20 compared to the PDMS, which is 310, right? So you have a large difference in thermal expansion coefficient. And then this is the so-called thermal biomorph, right? Under the same temperature, one elongate more, the other elongate less, and then it's going to form a bending, right? Form a bending. So this is a very well known, okay? And then we were able to get a very large bending. We were able to bend like three cycles, okay, 3 cycles, and then it's totally reversible. Okay? And then we demonstrate a number of applications, right, for robotics, for soft robotics, self-worker grip and so on. Okay, so we think soft thermal actuators has a lot of potential. Okay? There are a lot of actuators, right, for soft robotics. You have the pneumatic, right, it's pretty large, giant. You have to always have something attached, right, to apply the pressure or the liquid. And the others, right, you have the dielectric elastomers and so on, okay, which involves high voltage. So we think this thermal actuators has a lot of potential, but one problem is the downside is relatively slow. But we are working on some ways to improve that, to overcome the issue. Right? We can involve some mechanical instabilities and so on, work to improve on that. So hopefully next time I can update you. And then also we're talking about plant sensors, right? So in this case, particularly, it's the VOC sensor. Okay? It's a VOC sensor. It's a VOC sensor because VOC emitted by the plant can be associated with the physiological state of individual plants. Okay, so in this case, well, our nanowires basically used as electrodes, and then the functional device is graphene, and then with the ligand modified nanoparticles. Okay, so they're pretty much reversible because we use the hydrogen bonding and or halogen bonding, because these are reversible. Okay, and then so this slide shows the reversibility for different types of VOCs, and but also in this case also because this is a resistive mechanism. This is also very important to eliminate the effect of strain. Right, this is on the plant. Plant is going to easily deform. Okay, so we have to come up with ways to isolate the mechanical strain. So in this case, we use the what is called island bridge configuration. So the sensors you see here is the graphene sensors on the island, on the solid structures, and then in between here we have this called a bridge. This bridge, what we use we use the kirigami structure as the bridge, right? We talked about kirigami for the temperature sensor earlier. And then it works very well under the stretch, and the resistance has almost no change. Okay, and then here's just some demonstrations, mechanical stability. For instance, we use the fan to fan this is on the tomato leaves, right? So the resistance change is still very small. When the fan on is very small, you see this is the resistance change in percentage, right? It's less than 0.2% change. And then also we touch it. When you touch the leaves, you see this is gray. When you touch leaves, almost no change, right? It's quite gentle. Even though when you shake the stem here, we see a little bit of resistance. So anyway, this is important. Okay, this is important for a real plant sensors. Okay, yeah, this. All right, yeah, my time is up, so I will conclude here. So nanowire network represents an excellent material system for stretchable electronics, right? Silver nanowire we use for a variety of sensors for health monitoring. And then it brings new challenges in the manufacturing, right? Manufacturing, so we talk about several ways, okay? Method for manufacture to print nanowires. And then we demonstrate feasibility of recycling nanowire structures. This concept can be applied to other nanomaterials within the structural form of network. As long as it's in the form of network, okay, the concept applies. And then some other applications, right, we talked. Okay. And last but not least, I would like to acknowledge a list of former students and also current students and postdocs. Okay, so Dr. Shenshen Yao, or Dr. Zhen Cui now, and Amanda Myers, Dr. Qijin, Philippi, they were all former students. And then the current students, Yu Xian, Sean, and Adapan. And then also a list of collaborators. With Jin Yan and Brandon on the manufacturing aspect, and with Chen Shanwei on the plant wearable sensors, and then a list of collaborators on, especially right from some BME folks, Xiaogang Helen on the wearable sensors. Okay, and then acknowledge funding from National Science Foundation, Samsung, and the Assist Center at NC State, also the Plant Science Initiative at NC State. That's all I have. Thank you very much for your attention. And I'll be very happy to answer questions.
Okay, thank you, Professor Zhu. Thank you for your wonderful talk. You are using silver nanowires to demonstrate a lot of novel and inspiring and fancy applications. So basically, now our messenger, I wanted to pass some question from the audience to you. So here's the first question that in your stretching test of silver nanowire, you show in the first stretch and second stretch, they have a resistance change, especially before the strain is smaller than 50%, right? Mm-hmm. So yeah, in your very first of your slides showing that when you stretch the first stretch and second stretch, the resistance, exactly this one, you can see the resistance change increase a little bit for the second stretch. So so the audience wanted to ask for so here, so you got the silver nanowire length and also concentration matters here for this kind of performance. I mean, the initial stretch and the second stretch, this kind of performance difference, or this is just constant performance for all of the silver nanowire-based composite.
Okay, that's a very important question. I think the concept can apply to anything, right? To any nanowire length and any concentration. So this mechanism in general should apply, but the details could matter, right? The details could be different because here what we propose is relatively simple, right? We said there's a lot of details, right, to be uncovered actually. So for instance, so I basically say, hey, then probably there will be sliding between the nanowires and not between nanowire and nanometrics, right? There will be sliding, and then I said it cannot slide back. That leads to the wrinkling, right? The wrinkles here. But what happens is when you stretch, when the sliding happens, the wire itself, okay, it also gets stretched. The wire will also get stretched, and then it depends on the bonding, how strong the bonding between the nanowire and the matrix. Right? If the bonding is very strong, actually, we can break the nanowires. Okay, maybe we break the nanowires before the sliding happens. Actually, we found those. Because we try to understand those. We found those. If the bonding is very strong, that can happen. If the nanowires break, and then the behavior will be very different. Okay, if they break and then when they release, and then the resistance, I would say, will probably increase much more than what we observe here, and then it may not be a constant anymore. Okay, and then this is a complicated problem, okay? And then it's actually quite difficult because everything is embedded. It is difficult to do this. You see, personally, very interested in mechanics problem, try to understand it. But we have some understanding. We are still working on this, actually. This was 8 years ago, 9 years ago, but it's probably not totally solved. But anyway, so as I said, right, there could be other factors. So to answer your question, he's talking about the length and the concentration. I would say in general, this principle applies, but how much they will change, how will they exactly stay constant? I'm not sure. It depends, right? It depends on the ratio. If no wires break, then I expect maybe it will remain. But if some wires break, then maybe it will not be constant. And yeah, so maybe experimental speaking, in that case, you can do a few tests. About I think our experience is if you load unload a few times, it will becomes more or less constant. Okay, it will becomes more and more right towards a constant, and because it's sort of you have a sort of a training process. So the training process can help. And
okay,
yeah,
so
okay.
by following this
answers.
question, yeah, thank you for your answer. I think I get a point. So following a question, the audience also want to know how durable this type of stretchable conductor-based silver nanowires. So what are performance after the second stretching, for example, the third stretching, fourth stretching, how the curve should be like?
Yeah,
the recent change.
Okay, then it depends, right? It depends. If you stretch it, stay within 50%, then it's more or less constant. If you stay within 50%, but if you go beyond, and then it will go back. So you see here, I showed we actually we studied many cycles, hundreds of cycles, even thousands of cycles. You see, sorry. You see here, I'm showing the fifths and the 40th. You see, you see the resistance nearly constant up to 50%, right? And then for hundreds of cycles, we can have repeatable process. But so if you beyond that, then could be some other degradation mechanism could come into play, because this degradation, right, is also a process of accumulation. The damage is a process of accumulation. Typically, for any material, almost any material, right, the more like a fatigue, sort of like a fatigue, right? The more you do, and then the damage will accumulate little by little. Then you can, we notice when it goes beyond hundreds of like 500 or about 1,000, then we start to see a resistance increase a little more, right? It's not like as constant as we see here. But in general, it's actually very repeatable, reliable. The entire thing is reliable. It's not going to break. You're not going to see a huge change, right? It's very reliable in general.
Okay, thank you. So there's another question from audience that is that they want to know for the wearable heater. From the performance we can show the heater could be heat up to 160 degrees C. So is this performance reliable? Because the silver is embedded in a polymer matrix. So this kind of a high temperature will change the resistance of a silver nanowire and also the interaction between the silver nanowire and the polymer matrix here.
Okay. Very good question. Yes, but what the audience said is true, right? When you heat it up, the resistance of nanowire will change. But that's, I think, all contribute to the when we heat it up to this point, let's say 100 or 160, the resistance changes. Okay, definitely the resistance changes. We actually observe that resistance. We can use this as a strain sensor or as a temperature sensor. Okay, as a temperature. Definitely the temperature changes, but it's repeatable. Okay, if you turn it off, you see everything will go back, and then will go back, because this 160 is still far from the melting temperature of silver. It's also far from the melting temperature of PDMS. Right? PDMS can easily survive 200 degrees C and above. Right? So it's not going to cause 160 is not going to cause a permanent damage to either silver nanowire or PDMS. So the process and the performance is repeatable.
Okay, great. So there's one last question. So they have concern about the VOC sensor. So you're using the silver nanowire composite as electrodes to contact with graphene on the substrate. So how can you make sure the consistent contact resistance between the graphene and the silver nanowire composite consistent for each individual devices?
Okay. Okay. Very good question. Okay, all these are good questions. Okay, so the details, I wish my student Yushan is here. She probably can tell a little more details. But in general, well, I would say maybe there's a variation between devices. Okay, but for each device, it is repeatable, it is consistent, right? You can see here, we stretch many cycles and then the resistance doesn't change. That is not a problem, we do that. But I mean, between each device, maybe there's a slight variation, okay, in terms of the contact resistance.
Okay, so how about the stretchability? So if we stretch a device, does the consistent contact resistance change between the two?
I think so, because we don't know about the contact resistance. What we measure is the total resistance, because the total resistance, you can see, it has almost no change up to 50%, right? Almost no change. Yeah, almost no change up to 50%. So in this case, yeah, I think it is okay, because again here the major is because of this kirigami structure. Actually, the resistance, the contact resistance, the contact has very minimum strain, minimal strain on the contact. I think that is the key. That it contributes to this almost constant resistance.
Okay. Thank you, Professor Zhu. Thank you for your wonderful talk, and also you answer our question with a lot of technical details. So I think without further, due to the time limit, I think that's much of our talk today. Thank you very much for your time and to give us this wonderful talk. Yeah.
Thank you very much. Thank you very much, and it's my great pleasure.